for the invitation. Yeah, thanks a lot for the introduction and the invitation. I'm glad to be speaking today at this online conference. So I had announced, just like Sean, a title that's slightly different. My original title was Uniformization of Non-Positively Curved KLT Pairs. And I moved from non-positively to negatively, mostly for time reasons. So, I'm gonna be talking about this recent work with Benoît, Claudon, and Patrick Graf, where we have really two sides of the same story, one in negative curvature and one in zero curvature. And the techniques and the question and the important features are very different in both worlds. And so I decided to just focus on the negatively curved case. But if you're interested in the flat case, I'm happy to discuss that further along, or feel free to have a look at the paper. Okay, so I'm going to start with smooth classical setting. So this is really old material and results. So the setting is as follows. If I take a projective manifold, let's say n-dimensional, such that, okay, example, right, canonically polarized manifold. Then there's this theorem, mostly due to Yau, right, around 78, only about same year, that says the following. So if you consider the expression 2 times n plus 1 C2 the second Chern class of X, you subtract n times the square of the first Chern class of X, and you intersect that with n minus second power of Kx, then you always get a non-negative quantity. So this will come back a bit later, and I don't want to always write this. So I'm going to call this the Miyaoka-Yau discriminant of X. So this quantity is always non-negative. And so that's called the Miyaoka-Yau inequality. That was proved by Miyaoka for surfaces in a sort of like much general setting, and was obtained as a consequence of a Yau theorem on the existence of Kallenstein metrics, as I will briefly recall in a minute. So we have this inequality, and the focus of today's talk is really what happens when we have equality. And so the proof of the theorem of the inequality shows immediately that, more or less immediately, the equality occurs if and only if X is uniformized by the ball. And by this, I mean that X is the quotient of the unit ball in Cn. So Bn is the unit ball in Cn. And gamma is a discrete subgroup of holomorphism, discrete, acting properly and discontinuously. Here, actually, we're going to have even like co-compactness. And important point is that it acts without free points, so fixed point freely. Right. Okay, so this is uniformization. You can see this as a generalization in a way of Riemann or Poincaré-Kobe uniformization theorem in higher dimension. And right, maybe I can say a few things about the proof. So as I said, one of the key points of this proof is the existence of a Kallenstein metric by Aubin and Yau around the same years. so 74, 78. So there exists a calorimetric omega with Ricci -1. And then you have a computation that was done earlier by Chen and Ogi-Yue. I think it was 75. That says that if you have so in the particular case of an Einstein metric, if you compute this time not at a level of cohomology, but really at the level of classes. So I compute the Chern classes with respect to the emission metric omega of the tangent bundle. X omega, and I do wedge omega n -2, where omega belongs in the Chern class of Kx. This is pointwise equal to the norm of the trace-free curvature tensor of the tension bundle multiplied by the top power of omega. Okay, that's because usually there's another term, but that disappears when omega is Einstein. And so this is a pointwise inequality, and now I can integrate over x, right? And what this tells me is, well, certainly this is non-negative. And the equality case happens exactly when Tx has constant curvature tensor. And that means that omega has constant bisectional curvature, which now we know very well is equivalent to x omega being uniformized by one of the three model spaces, and in negative curvature, the model space is just the unit ball in Cn. And this is how we get the universal cover of x is the ball. Okay, so this is the proof, one possible proof of that inequality and the characterization of equality. Now, a few years later, in 88, about 10 years later, so Simpson published a few really fundamental papers. One of them aims at sort of providing a different view on uniformization, mostly inspired by the case, like so Hitchin's paper in the case of curves, how we can use sort of variation of fuzz structures to detect uniformization. The reason I'm mentioning this is it's going to come up later when we move to the singular setting, where it turns out that a clever combination of the original strategy of finding a Kehl-Einstein metric and Simpson's strategy for uniformization does actually generalize to the single setting. So his observation, what he proved is, okay, so remember Kx is ample, and that implies by the existence of a Kehl-Einstein metric, implies that Tx has an Hermite-Einstein metric by the symmetry of the Ricci tensor. And so that implies that Tx is Kx polystable in the sense of Mumford, slope stable. Okay, and this uses Aubin-Yau, right? And so Simpson's strategy is that, okay, now if I just remember from the ampleness of Kx and the Kehl-Einstein metric that Tx is polystable, then you can give a completely differently flavored proof of the uniformization theorem. And the way it goes, I'm not going to at all go into the details because it's a bit lengthy, but the idea is that out of Tx, one can construct another vector bundle, actually a Higgs bundle, Okay, is that so crazy? E is essentially the endomorphism bundle of direct sum Tx plus the trivial bundle Ox. That satisfies three properties. Sorry. The first one is E is H stable or polystable as a Higgs bundle. And the second property that's important is that C2 of E vanishes as well with C1 of E against H. Swan here, H is just Kx. And so Simpson's general machinery in that particular case tells you that there's somewhere a complex variation of a structure. And the particular case of this, okay, so it means that it is induced by a complex variation of a structure. Actually, this vector bundle E is much more particular than just any vector bundles. It's an additional structure that guarantees that actually we have a paired map from the universal cover of X that lands directly in Bn. Bn is just Pun1, the automorphism group by the stabilizer of a point. Right, and you see the N1 is sort of related to the decomposition of E as Tx plus Ox, but I won't say much more than this. And that period map is actually a cover. So a local local, so it's our cover. So in particular, it is isomorphic. Okay, so this is how Simpson sort of reproves uniformization for the varieties with Kx ample and satisfying the Miyaoka-Yau equality. Okay, and now that's maybe where I want to stop for the smooth setting. So let me move on to the singular setting. And I want to sort of justify why we're interested in singular stuff. So in this particular setting, in this particular question, it's actually not complicated to see why. So if I consider a quotient Bn mod gamma, where this time gamma might have fixed point. Then this has two implications. Let's call this space X. So the first consequence is that X might not be smooth anymore. It could, but in general it won't. And Kx might not be ample anymore. It might have fixed point, but still acts co-compactly. Kx might not be ample anymore. Okay, but you may still want to sort of have a criterion that tells you, okay, I have a single space. When is it globally given as the quotient of the ball by some discrete automorphism group? And so you sort of have to analyze what fixed points sort of change and what kind of geometry additional geometry they involve. So it's one way to maybe consider this, to approach this, is by using famous lemma, so Zelberg lemma. Here, gamma is not any group; it's a subgroup of Pun1, so it's a linear group. And so it tells you that there exists a finite index subgroup that's torsion free. And here, since gamma acts properly discontinuously, being torsion-free implies that gamma prime acts without fixed points. And now, okay, move up. Now this is quite nice because it means that there's one intermediate quotient. If I start from the ball, then I have an état map from the ball to the first quotient by this slightly smaller subgroup gamma prime. This variety, maybe I'm going to call this guy Y. This is a honest état quotient of the ball, compact projective manifold with ample canonical bundle. And then I take another finite cover to my variety that I'm interested in, so that I called X earlier. Maybe I'll give a name to this map, pi. All right. And okay, what do I do with this? So the first observation is X has a finite cover that's smooth. Okay, so that implies that X has quotient singularities. Okay, which might not have been completely obvious from the shape of X at the beginning. And the fact that, so that's one thing. And so pi is a finite cover. It has ramification in general. So there are two types of ramification that are possible. If you look at the fixed locus of the Galois group on acting on Y, if you want, then there might be a codimensional one part. And that part has a different role from the rest. So pi in general is ramifies in codimension 1, which means that I can find divisors delta 1, delta n, so divisors, via divisors on X, and integers mi, such that pi ramifies generically at order mi along delta y. And if you write the canonical bundle formula, that just means that the pullback, the ky is the pullback not of kx anymore, but of this divisor delta given by the sum of the delta I weighted by the multiplicities 1 minus 1 over mi delta I. Okay, so this is very classical. Okay, so the two things that are new is now my ball quotient as singularities, orbifold singularities, and the natural bundle to look at that's going to be ample is not the canonical bundle anymore, but it's this log canonical bundle kx plus delta. Well, delta is completely determined by the ramification of our group in codimension 1. Okay, so that leads me to two definitions. Okay, so X delta is going to be what people call a complex orbifold. So a complex orbifold X delta is a pair where X is a normal analytic space, complex space, and delta is of the form standard coefficient. So delta I is a val divisor, and mi are integers at least 2, such that locally on X there exists cover. So there exists subsets X alpha covering X and a cover up Y alpha X alpha finite cover. Let's call this by alpha, such that K y alpha is the pullback, so it ramifies x alpha plus some. And y alpha is smooth. Okay, so complex orbifold, if you want, if delta equals 0, is just an analytic space with finite quotient singularities. And we like to also have a boundary divisor weighted by those weights 1 minus 1 over mi, to remember that actually the way how we express x as a finite quotient of a smooth space actually encodes dimensional 1 ramification. Okay, so, and the result of this is Bn mod gamma endowed with this ramification divisor delta that I defined earlier is a complex orbifold. So I'm gonna make a small pause here and look at the first theorem that I stated. That says, okay, if you have a projective manifold with kx ample, then you have a Miyaoka-Yau inequality. Inequality happens if only if x is Natal. The universal cover of x is the ball. Now, if I replace x here by a pair of a complex orbifold, projective orbifold, such that kx plus delta is ample, I can make sense of orbifold term classes. I'm going to have the same inequality, and I'm going to have just as much a characterization of equality by being an orbifold quotient of the ball in the same way as in the smooth case. So we can slightly enlarge the category of projective manifolds to the category of projective orbifolds and have a uniformization criterion that will be just the same. Now, this is where I'm jumping to a slightly bigger class of singularities that sort of naturally arise in birational geometry and called log terminal, or in this particular case, Kawamata-log terminal singularities that are more general than finite quotients, but that in a lot of ways behave similarly. So if I have a pair, x delta, where x is a normal complex space, and delta Q divisor, I say that this pair has Kawamata-log terminal singularities. So KLT for short. If locally on X, so there exists a trivialization. Let's call this sigma of a certain multiple of kx plus delta, kx reg. Okay, this is going to be confusing. I write like this. So kx plus delta is a Q divisor, and there exists a trivialization of this line bundle sigma such that the integral over x reg minus the support of delta of sigma, so I have to wedge sigma bar. This is not quite a volume form, but I have to take m through it, and this behaves like a volume form, so I can integrate it over, let's say, a germ of any single point of x, and I want this to be finite. Okay, so since I remove delta, I can view sigma as m polynomial forms with poles along delta. Okay, so I can integrate it So this is KLT pairs, okay? And a remark is a complex orbifold X delta has KLT singularities. So eventually the question will be, all right, given a KLT pair, maybe with good coefficients, is it possible to detect whether that KLT pair is actually a Boole quotient? So another remark that's very important is that if X delta is a KLT pair, except dimension n, probably I need delta to have standard coefficient. So of the form 1 minus 1 over m. Then there exists a very small Zariski closed subset. And by very small, I mean the codimension of Z inside X is at least 3. Okay, so if X is a surface, Z would be empty. And there exists such a Zariski closed subset, such that away from Z, it's just a complex orbifold. Okay, so one way to say this in like other terms is that if you start from a KLT pair with standard coefficients, in codimension 1 it's smooth, in codimension 2 it might not be smooth, but it will have at most finite quotient singularities. Okay, this enables to define some term numbers like C2 of X delta against H in minus 2, if F, so in the projective case, right? So H is an ample line bundle, or any line bundle really. Projected. In a way that a couple of properties, of usual properties, are satisfied. So the first one is if X delta, so this is a rational number. If X delta is a projective orbifold, then this is just coincides with orbifold Chern numbers, the usual orbifold Chern numbers. Okay, so that's good news. B is that you have a restriction. So if you have S, a general complete intersection surface, S is H1, Hn minus 2, and Hi are in H may be very general. You can assume H is very ample if you want. Then C2 of X delta times Hn minus 2 is nothing but if you have this bundle that I have not defined, that will not define, but that's the equivalent of the tangent bundle, tangent sheaf for pairs. So it's not really a sheaf, but it makes sense as an orbifold bundle, and I can restrict that to S. It's an orbifold bundle on the orbifold surface S. Okay, and yeah, this restriction formula just as in the usual setting. And C, if let's say delta is 0 and X is smooth in codimension 2, then this Chern number is nothing but C2 of X Hn minus 2 coincide with the second Chern number of any resolution if P is a log resolution. Okay, so this construction is due to Mumford in the projective setting. There are analog in the complex analytic case that I'm not going to discuss. And the upshot is for k-LT pairs, we're able to define Chern numbers. Not all Chern numbers, but the C2 and the C1 squared. Okay, and so given what I've said before, question that's probably natural is that given a k-LT pair, projective k-LT pair x delta with standard coefficient, is there a numerical criterion to characterize Bull quotient? Okay, so that's the question, and the theorem that I want to explain today is an answer to that question. So again, that's a collaboration with Claudon and Graf. That says the following. So x delta projective pair, k-LT pair with standard coefficient. Then x delta is a Bull quotient if and only if two things happen, just as in the smooth case. Well, first of all, we want kx bel delta to be ample, right? You remember, maybe I can move a little bit further up in the text. Right, here. If you have a Bull quotient here, Bn mod gamma, then you have this ramification formula that tells you that the canonical component of y, which is ample because the Bergman metric on Bn descends to a positively curved metric on ky, and ky is the pullback of this bundle k plus delta on x, and because pi is finite, then ampleness descends. And so you know that Bull quotients have to be, once you consider the boundary divisor, have to be canonically polarized. Okay, so this is not very surprising. And the second condition is that we have Miyaoka-Yau equality, so 2n plus 1 C2 of x delta, which I have not defined. And lack of time. And minus 2 is 0. Okay, so that is the theorem. Okay. So this theorem does not live in the vacuum. It has a lot of history and a lot of contributors in different slightly less general situations. So I'm going to try to do a good job, maybe quoting who proved what earlier. So all remarks. So if delta is 0, so first of all, if delta is 0 and x is smooth, it's just the Miyaoka-Yau uniformization here, right? Now, if delta is 0 but x is k-LT, so this was proved by Grébecus, Eternel and Tadji over a span of 3-4 years. A series of 3 papers with various degrees of generality. I want to say a little something here about how they prove this theorem. So as I said, it's like a series of 3 papers. There's a lot of material. It's very technical. There's a lot going on, but I want to single out a few important facts or key parts of the proof or key actors in the proof. So the strategy, in part, in a way, it's not a uniformization theorem. It's a theorem from singularity theory. What they prove really is if you have equality in Miyaoka-Yau inequality, then X has to have quotient singularities. And from there, you can just apply the usual orbifold Miyaoka-Yau uniformization theorem. So what they prove really is a singularity theory. It's singularity theorem. They show that X has quotient singularities. Once you know that, then you can use orbifold by Yau if you want. Okay, so the core of their work is to achieve that. And as I said, if you try to follow the original proof with the Chern class computation with the Kallenstein metric, then it sort of comes short. Essentially, let me go back in time. So in singular settings, we have singular Kallenstein metrics, and they're really nice, but we don't really understand them near the boundary, near the singular locus. Okay, so we would have a pointwise equality like this one on the regular locus of the variety with the adapted like Kallenstein metric. The problem is if we don't know if we can integrate those quantities and if it gives us what we want. Okay, so that proof, it sort of collapses pretty quickly in the singular setting. Okay, and this is where using Simpson's approach is fruitful. But Simpson's approach, if you remember, it needs some input, and that's the stability. So the first step to implement Simpson's strategy, which is in a way much more robust, is to show that Tx is semi-stable. And this is sort of the main keyword of the conference. So that's why I emphasize this. The semi-stability here doesn't come for free. Here, you actually need, as far as I'm aware, the only proof of semi-stability in that context is through the singular K metrics. Again, that's something that I proved a while back, 2015. Okay, so that's really the beginning, right? So you have your variety, KLT singularities, Tx is semi-stable, and then you want to see that if Miyaoka-Yau inequality is an equality, then you want to show that the variety is smooth or has quotient singularities at most. And a key input comes from the MMP, is that the topology, the local topology of KLT singularities sort of resembles quotient singularities. It's very vague. I apologize for that. One statement that I can give, that's sort of the ultimate statement, is that if you take a KLT germ and you look at the regular part of that germ, then the fundamental group of this regular part is finite, just as for quotient singularities. Okay, so this is thanks to big progress in MMP theory, and I think this was the first result in that direction was proved by Chen Xu, and then GKP, 3 German from that paper, they sort of built on that to improve, or let's say rephrase the statement in a more geometric way. And then the final piece was proved by Brown in 2019, where he proved exactly what I said, the finiteness property of the local fundamental groups. That's really the new input that really unlocks this whole business and enables to go through with the strategy. But that being said, like, this is still a very difficult theorem. These are the main points. All right, so I don't have a lot of time left. So I'd like to make just a tiny remark and then give a few ideas involved in the proof. The other remark is that, so there is a Miyaoka-Yau inequality. So if x delta is KLT with standard coefficient, DLT would actually work. And kx plus delta ample, and again here, you could replace, there's a statement with just nef. Then 2n plus 1, we have the inequality that you expect. Okay, and that was proved by myself and Taji in 2016. Okay, so here again, just like in the smooth case, we have a very general inequality for inequality pairs. And the equality case specializes to Bol quotients. Very well. Okay. So the proof relies a lot on what has been done before. Okay. It's sort of putting everything together in the proper order. And it's actually a bit more difficult than it sounds. Like when I first started to think about it, I really thought this would be quite trivial, and it ended up being not so trivial. But the idea is very simple. And the key point that's is to construct a cover, a cyclic cover. Y to X, so in the situation that I'm working with, right? Projective KLT pair, K plus D ample, if you want. And I want to construct a cyclic cover that satisfies two properties. So pi ramifies exactly at the right order, at order mi along delta I. So we're really happy that ramification along delta I is exactly what we need to cancel those like annoying poles. But of course, the world is not so perfect. So in general, there's no cover that ramifies in codimension 1 just along those delta I that you picked, right? You always have some extra ramification, and that's annoying. That's the source of all the problems. So the extra ramification in codimension 1 is supported along a general element, of a very ample divisor H, very ample system. Okay, and so let's go n the ramification order. So I have a cover that will do this. Unfortunately, I have to add ramification, and if n is the order of ramification on H, I have this property. Okay, and that implies, since H is general, very general, that Y is KLT. Okay, and it's important that H has a lot of freedom. H moves in a base point free system. And so this enables to get rid of all the annoying like orbifold stuff of sheaves that are not really sheaves. So it enables to work with actual sheaves. Right, Tx delta, which is not a sheaf at the level of X, it's an orbifold sheaf, becomes honest sheaf on Y. Unfortunately, it's not a tangent of Y because of that extra ramification. Okay, and that's part of the problem. So that's the key points. We construct this. As far as I'm aware, in this degree of generality, with no assumption on delta i's, I don't think the existence of such a cover was known, but it's essentially follows from Shakurov, the construction of Shakurov. And then my time is over, so I'm just going to say that so using GKPT, so not the statement itself, but what they prove in the paper, we can actually prove that Y minus pi inverse of H has quotient singularities. And so does X minus H. And since H varies in an ample, very ample system, and in particular base point free, that implies that X has quotient singularity, or the pair X delta, maybe I should say. And so we are back to the case of complex orbifolds where the story is very well known. And that finishes the proof. Okay, so thank you very much.
Thank you for the talk. Is there any question or remark from